Hey, welcome back, guys. So we are left off with alkenes. So I'm just gonna go through the chemical properties and the general reactivity of alkenes towards electrophilic reagents. So for the general reactivity towards electrophilic reagents, I would like to draw the structure of alkene first to show you how it looks like. So this is how alkenes generally look like. It would have a CC double covalent bond with a pi bond as well as a sigma bond. And they are generally more reactive than alkanes, and it is due to the pi electron cloud between the doubly bonded carbon atoms, which suggests that when there's a double covalent bond, it will have high electron density. Okay? And as you can see in the second bullet point, unsaturated CC pi bond is a region of high electron density that attracts electrophiles to form a single larger saturated organic product. So you notice that most of the electrophilic addition of alkenes, they convert the double bond into a single bond. So that is why we call them saturated. Alright, so then the third bullet point, you see that the reason why they are very reactive is because of the loosely held pi bonding electrons that attract the electrophiles or even induce dipoles in and create electrophiles in some nearby molecules. So I'll show you later on some electrophilic addition reactions whereby the electrophiles, they are molecules in which both the covalently bonded atoms are of the same electronegativity, and yet they still are able to act as electrophiles. And that is because these pi bonding electrons, they are able to induce the dipole. And the reason why they are loosely held is because of the weak pi bond. Alright, and the weak pi bond is because of the less effective overlapping of p orbitals. Because as you can see right here, right, the if you draw out the orbital diagram for ethene, I'll use one note to draw for this. So you can see that I'm drawing the hybrid orbitals, the sp2 hybrid orbitals. And then I'll draw the p orbital. So you see that the p orbital are side overlapping side on, whereas the sp2 hybrid orbitals, they are overlapping head on. So this one is a sigma bond and it has a head on overlap. Whereas the p orbitals, they are unhybridized, they are overlapping side on. And because of that, the degree of effectiveness of the orbital overlap is not as effective as that of a sigma bond. Because as you can see, the electron density is accumulated away from the internuclear region. Okay, so for the summary of reactions, you guys can take a look and remember the RNC by heart. But I will just go through the RNC and help you guys understand and appreciate a little bit better. So the first one is uh a reduction reaction. So as you can see, I give you the chemical equation and I give you this reactant and I ask you guys to predict what kind of reaction is being is taking place right here. So you see that the double CC bond is being converted to a single CC bond. Okay, where two hydrogen atoms are added to the double covalent bond. Okay, so because of that, we call this a reduction reaction whereby the the reactant gains hydrogen. So the gain in hydrogen is represented by a reduction reaction. Okay, so the reagents and conditions are as shown here. So hydrogen gas, you use nickel catalyst, or you can also use platinum or palladium catalyst. And take note that the conditions for each of them are different. So if you use nickel, you have to heat it up. If you use platinum catalyst, you have to use it at room temperature. One interesting observation, if you look at your data booklet, right? Let me see, where's the data booklet? Ah, yes, here. So you see the data booklet, you realize that nickel, platinum, and palladium are on the same group. They are all on the same group. Alright. So in this case, the palladium and platinum catalysts, these elements are at a lower in the group 10 compared to nickel. So I believe that you have to use heated nickel catalyst is because there is less vacant energetically accessible d orbitals compared to that of palladium and platinum. So for this case, nickel, you have 3D, but for palladium and platinum, you also have 4D and 5D. So that is why. Okay, and you know how because this catalysis reaction is actually a heterogeneous catalysis reaction, so in a sense, you have to make use of the vacant energetically accessible orbitals to act as your active sites. So that is why it's very important to take note of why these uh, catalysts are either being heated up or used at room temperature. Alright, let's move on. To take note that COOH, carboxylic acid group, is not being reduced right here. It can only be reduced using lithium aluminum hydride in in dry ether. Okay? And that is because your lithium aluminum hydride, they produce this hydride anion which acts as a nucleophile to attack the carbonyl carbon. This is just some extra stuff you can take note of. So the hydride anion will attack the carbonyl carbon and this will form this tetrahedral intermediate right here. Okay, so after this, then you would use water. Okay, and this would in turn give you this. in which this one will leave as a leaving group, and the lone pair on the negatively charged oxygen will come down here, and that will help you form your aldehyde. Okay, so this is just some extra knowledge if you would want to know, and it's tested in exam. I remember there was a A-level exam question in 2022. They asked why carboxylic acid group is being reduced by aluminium, the lithium aluminum hydride, whereas the alkene is not being reduced by lithium aluminum hydride. So in this case, you have to explain that because carbonyl carbon is partially positive and is very electrophilic because of the very polar CO double bond, that it will be able to attract the negatively charged hydride and ion. Whereas the CC double bond is non-polar, so it's because both of the atoms are of the similar electronegativity, and thus they don't have any nucleophilic, they don't have any electrophilic sites that the negatively charged hydride and ion can attack on. So that is why you can't use the hydride and ion to attack the carbon of alkenes. Okay, let's move on. I'll erase all this. Okay, next up is electrophilic addition. So in this case, I present you this chemical equation. C2H4 plus X2 gives you this product. So you just rewrite this chemical equation into the organic structures of reactants and products right here. So then the reagents and conditions is the halogen under standard state. So you can see that chlorine is in gaseous phase because it's at standard state at gaseous phase in the sense that at under standard condition, or you can say room temperature, your chlorine exists as a gaseous form and your bromine exists as a liquid form under standard condition. Alright. And you have to use tetrachloromethane solvent so that you won't have any side products being formed. If you have water in your solvent, then alcohols may form as a side product. And the absence of UV light is to your prevent free radical substitution. Because your alkenes also contains your CH bonds, which can undergo free radical substitution with halogens. And this occurs under room temperature and pressure. Because your CC pi bonds are very weak and they break easily with little energy they break easily in a sense. So less energy is required to break the CC pi bond. The observations, you link it to the chemical equation. So, and the mechanism right here. So you see that the CC double bond, then as what I said earlier, how the loosely pi bonding electron induces dipoles and create electrophiles in molecules that have the same electronegativity. So you can see, for instance, Br or ClCl, they have the same, they contain atoms that are covalently bonded. They have the same electronegativity. But it is the pi bonding electron right here, or the high electron density of the CC double bond, the pi electron cloud, the nucleophilic pi electron cloud is able to polarize the halogen such that you can see that because this part, right, is very, it has high electron density, and you know that like charges repel. So if you know like charges repel, all my electron density would shift towards this area. So this part is the part that has slightly higher electron, whereas this portion right here is the part that have lesser electrons. Okay? It's based on the concept of like charges repel and unlike charges attract. So after the nucleophilic pi electron cloud is able to polarize the XX bond, it will cause, it will attack the electrophilic halogen atom that is has a partial positive charge, and uh it will heterolytically break the XX bond to form your halide anion. So this halide anion will then attack the carbocation that is formed. So you have to take note that the arrow should be pointing towards the carbon. Okay? S- And take note that you have to write slow and fast reaction. Alright? So the slow step is due to the heterolytic fission of the electrophilic molecule, and it's also due to the breaking of the pi bond, which require high activation energy to overcome. For the fast step is because you can see that there are strong electrostatic forces of attraction between the halide anion and the carbocation. So that is why it is the second step is the faster step. Okay, let's move on. So this one is a bit of a tricky reaction. Uh, you have bromine in aqueous state, aqueous bromine and sodium chloride solution. So the very first step, um, you know that this reactant contains a CC double bond. So this CC double bond, that means I need to use this nucleophilic pi electron cloud to polarize something. So there are two different. Okay, so what are the chemical species that is in my reagents? Which is BrBr. There's also H2O. There's sodium, and there's chloride and ion. So the only possible electrophiles are BrBr and H2O. Sodium cation, some people may argue, is a positively charged and thus is electrophilic, but I wouldn't say this is a strong electrophile because it has low charge density. This one have a very low charge density. This is a recap back in period 3 notes where they say that sodium cation, they have a low charge density and thus they cannot undergo hydrolysis. Okay? So with BrBr and H2O as your electrophiles, you must be wondering which one should I use as a electrophile. Correct answer is you have to use bromine as your electrophile. For H2O, right, is because which one we have to look at which bond is easier to break. So in this case, this bond has a BE of, we'll look at the data booklet. So the BrBr have a bond energy of 193, OH is much higher. So OH you can see is OH. Okay, it's 460. So that is why I wouldn't recommend using water as the electrophile. Alright, so in this case, bromine will be our electrophile, and we'll use the pi electron cloud to attack the electrophile. So right here, this one gets attacked by the nucleophilic CC double bond, slow step, and thus carbocation and bromide anion is formed. Then the bromide anion can attack the carbocation to form this product. However, you take note that the reagents, we also have chloride anion and water molecule. Both water molecule and chloride anion, they contain a lone pair of electrons that can attack the carbocation. So they can also act as nucleophiles. So you can see water and chloride anion, they are able to act as nucleophiles where they use the lone pair of electrons to form a dative bond, or in the sense you can attack the electrophilic positively charged carbon of the carbon cation. Okay? And then an extra step you need to note if you're gonna use water as a nucleophile is that you have to attack, you have to, you will need to break the OH bond so that I can form my alcohol. So to do that, I will use bromide anion or chloride anion, or you can also use water. You can also use instead of that you can also use water. There's a lone pair. You attack the hydrogen right here so that I can heterotically break the OH bond. Alright. In this case, the observation you see that uh take note that in aqueous phase, the color will be different. So in this case, orange aqueous bromine decolorizes, and steamy white fumes of HCl and HBr will form. Okay, the orange for liquid bromine, it will be orange red. So just take note of that. All these colors can be found in the data booklet, so you don't have to worry too much about memorizing the colors. Save you time, man. Okay, so now we'll see that this is the reactant undergoing electrophilic addition because there's a CC double bond and water is used as a reactant to form an alcohol. Alright, you take note that the OH goes to the carbon that is more substituted, but the hydrogen of the water goes to the carbon that is less substituted. Okay, and these are the reagents and conditions. Note that because remember we are talking about how water is not a very good electrophile because of the strong OH bond. Yes, that is why we have to use much harsher conditions, which is concentrated H3O H3PO4 catalyst and at a very high pressure and high temperature. Alternatively, you can also use concentrated sulfuric acid at room temperature, followed by water and heat. Okay, so I can show you how this two reaction mechanism work just for some extra knowledge. Let's see, where did I put the thing? Okay. So we start off with concentrated H3PO4 first. So we have the CC double bond. Okay, we see what reactant we use right here. Uh, alright. So we have this. And because I do not want to break the strong OH bond of water, that's why I would rather break the OH bond of the acid catalyst. Okay? And this is because these catalysts, which are acids, they are more acidic than water. That is why they are much more able to be readily reacting with the nucleophilic alkene. So this is concentrated H3PO4. Okay, so this is then you oh heterolytically break the OH bond so that I form this. Okay, so I'll form this carbocation that is very stable due to 3 electron donating groups increasing the electron density of the positively charged carbon of the carbocation. And we'll see that a stable leaving group right here is being formed. You see that a stable leaving group is being formed. And this is because the p orbital of oxygen overlaps with the pi orbital of p double bond O. And this causes resonance stability. So this is a resonance stabilized molecule. And you know that since this is resonance stabilized, this causes the POE of the reaction to shift much more to the right. And that is why this step is very much favored. Okay? Then the next step, usually we would use water to attack the carbocation. We will just use water to attack the carbocation. And this causes this reactant to form. Sorry, this causes this product to form. And since this is a catalysis reaction, I will want to use the deprotonated phosphoric acid to gain back that hydrogen atom. To gain back the hydrogen atom. Okay? And thus this will help us form the alcohol as well as form back the H3PO4 catalyst. Alright, so another thing is the sulfuric acid. So I'll just use what is it called? The skeletal formula so that it will be much faster. In this case, sulfuric acid is because it's more acidic than water. That is why it can be used as a electrophile where the hydrogen is more electron deficient. Okay, so this hydrogen right here is more electron deficient compared to the hydrogen on water. And it is because of the fact that there's many electronegative atoms that is pulling the electron density away from the hydrogen for acids in this case. A good practice is to label the dipole. So in that above example, I should have labeled partial positive charges and partial negative charges. Just saying, in the exam, I don't think this would be tested or within your knowledge, but it can be tested as the application question. So this just helps to give you guys more exposure. So this one will be a positively charged carbocation, and I will be able to form this leaving group. And like H2PO4 minus, a H2PO4 minus, this is also resonance stabilized, which causes the POE of the reaction to lie much more to the right. Okay, so now, oh yeah, I forgot to label this fast step. Alright, so afterwards, we can alternatively, you can use water to attack the positively charged carbocation, or you can also use this to attack. And you use this to attack is because the negatively charged and the positively charged, they have a strong electrostatic force of attraction, and that is why they preferably want to attack each other. So this will help to form this product. Okay, so what's next? What's next is you know that this group right here contains many highly electronegative atoms such as oxygen. So in this case, it causes di causes a net dipole moment of the CO bond right here, and this results in a polar bond that has a partial positive charge on the carbon. Okay, this one should be negative. And thus, you can see that water acting as a nucleophile, I can attack the electrophilic carbon right here so that I'll form my alcohol. Okay? Okay, I'll go on to the next reaction, which is this reaction right here. So this one is I would say most people would forget about the alcohol to new to substitute the alcohol group with Cl. So just take note that alcohols also undergo nucleophilic substitution with HCl to form halogenyl alkenes right here. Okay? And your CEC double bond will attack the electrophilic hydrogen of HCl to form the stable carbocation, and it will be attacked by the nucleophilic chloride anion. So look at where the arrows are going. So HX or HCl, in this case, they are already polar in nature. So there's not much the nucleophilic pi electron cloud can do to induce the dipoles since the dipoles are already there. And take note that the carbocation form is this carbocation right here instead of this carbocation. Some people will say that this carbocation is a tertiary carbocation what, so 3 electron donating group. However, take note that the unhybridized p orbital on the positively charged carbon right here can actually sideway overlap with the pi electron cloud of your benzene ring. And this causes the delocalization of pi electrons from the benzene ring into the positively charged carbon of the carbocation. Alright, so that is why it disperses the positive charge to a much greater extent because resonance effect usually is a lot stronger than the inductive effect. So just take note, this Markovnikov rule is very important in terms of deciding what product is being formed as the major product. So when an unsymmetrical alkene goes through electrophilic addition, the main product is one which the hydrogen atom attaches to the less substituted carbon. So the main idea is that you want your carbocation to be the most stable. And how you do stabilize it is through either electron donating alkyl groups. The more electron donating alkyl groups, the greater the extent to which the electron density on the positively charged carbon increases via the inductive effect, and this disperses the positive charge to a greater extent, thus resulting in a more stable carbocation. Alright, uh, and the stereochemistry is that there's an equal probability that the nucleophile attacks from either side of the plane because you know that the carbocation is a trigonal planar structure. Okay, so you have to state that the carbocation is a trigonal planar has a trigonal planar geometry, and there's an equal probability of the nucleophile attacking the electrophilic carbon from either side of the trigonal planar structure, and forms equal amount of both enantiomers, which is a racemic mixture, and thus there's no net rotation of plane polarized light because they rotate the light in opposite direction but to the same magnitude. Okay, this reaction, I'll go through this reaction in the halogenyl alkanes topic, so not to worry too much. Oh, this one, I will go through this one because this one is actually supposed to be under alcohols. So just take note that these are the reagents and conditions being used for elimination of alcohols to form your alkene molecule. The third RNC on concentrated H3PO4 heat at 200 to 250 degrees Celsius. Um, I think some schools do put this, but the most common one is definitely excess concentrated H2SO4, and AlO3 solid. And the reason why we use these two is because they are very good drying reagents decrease, that helps to absorb this water. Alright, so since water goes down, sorry, the number of moles of water go down in this case, that's why your POE can shift to the right. Okay, so AlO3 actually contains the Al3 plus and O2 minus. So Al3 plus has a very high charge density. Okay, so high charge density, and it is able to absorb the water molecule very readily. For mild oxidation, mild, in this case, you have to add OH on both sides of the C double bond. And cold, and the condition is actually cold. Okay, so KMnO4 is being used as the oxidizing agent right here, and these are the acidic and alkaline mediums that are used. So the reason why acidic and alkaline medium are so important is that in the acid medium, you would actually reduce MnO4 minus to Mn2 plus ion. But for alkaline medium, you are reducing MnO4 minus to MnO2. You can actually search this up in the data booklet. MnO4. In acidic medium, you go to Mn2 plus. So this is how the purple KMnO4 decolorizes. Whereas if you use an alkaline medium, you are actually forming manganese dioxide. Okay? So you just take note that if you use an acidic medium, the change in oxidation state is actually from +7 to +2. So a -5, and this is +7, this is +4, it's only a difference of 3. So you can see how using different mediums, either acidic or alkaline, can cause different change in oxidation state between the two species. So because it's in cold condition, the reagent is only strong enough to break the pi bond instead of the sigma bond. And how do you balance this equation? Let me show you right here. So I'll use OneNote again. In case you couldn't remember how to balance this equation, right? This is how you balance it. So you have H3C. This can be either cis or trans because I never really specify it. And this causes this product to form. So you see that there's 2 oxygen, okay, and 2 more hydrogen being added. So since there's 2 hydrogen being added, I will want to add a water molecule on the left hand side. Add a water molecule on the left hand side. So you have 2 hydrogen here. Then the next step is, since we are using an oxidizing agent, we would have to represent a gain in oxygen using this symbol right here, a bracket with an oxygen. So in this case, how many more oxygen we need to add is 2 more. So on the left hand side, we already have one oxygen that comes from water and another oxygen that comes from the oxidizing agent, that is KMNO4. Okay, so this is how you form the chemical equation for mild oxidation. Last but not least, we have strong oxidation or oxidative cleavage. So in this case, uh, we have, oopsies, we have the same, but just that it's heat under reflux, so that you can fully break the both the sigma bond and the pi bond of the alkene. Alright, and as you can see in this reaction right here, I would help to show you how this is being done. So we have this over here, right? So if I want to fully cleave both sigma and pi bond, I'll cleave at this part, I'll cleave at this part, I'll cleave at this part, I'll cleave at this part. Okay? And then we add oxygen to that double bond. Okay? I'll shift this to make it more clearer. Alright, so as you can see, I have these two organic products, and we also have to add. Originally, it's actually this, but because we are oxidizing it further due to the strong oxidizing agent of KMNO4, we add the oxygen to each of these hydrogens. Okay, so in the sense that if you have a terminal alkene, they will be oxidized. This, like example, this terminal alkene, it will be actually, this is what will happen. Okay, and then if you oxidize it further to become carbonic acid. And this carbonic acid can be converted to carbon dioxide and water. Alright? Okay, so another thing you take note is that if you have two alkene bonds that are adjacent to each other like this, it will form this product called ethane 1,2-dioic acid. So when you see this, you have to make sure that it is oxidized further, because the CC bond, this CC bond is actually weaker. And why is it weaker? It's because of the delocalization of electrons. You see that there's a p orbital right here, there's a p orbital right here also, and then there's a pi orbital of CO bond. And this sideway overlap causes delocalization, and this bond is actually weakened due to the delocalization as well as the inductive effect of the highly electronegative oxygen. Okay, so the ethane 1,2-dioic acid will actually be oxidized further. It will become 2 carbon dioxide and water. Alright, so 2, 4, oxygen 1, 2, 3, 4. Okay, yeah, so something like that. Uh, I think this one, right, it's not fully correct. And that is because my ethane 1,2-dioic acid will form this anion right here. And this anion cannot be further oxidized into carbonate, just to take note. So let's try to redo this part together. So this is how you balance it. Okay, so we will form ethane 1, 2, we'll form this anion, and then we'll also form this also. Oh, this, we don't have this. Okay, I see, okay. This is the two organic anions that we'll produce, and then we'll have, remember the carbon dioxide that is formed from the oxidation of the terminal alkene? That one will become carbonic, sorry, they will become carbonate anion. So given this information right here, right? So we will count the number of carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we'll count here. 1, 2, oopsies. We'll count here. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 carbon. Now we can check for oxygen. Alright, so we check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 oxygen right here. Then we check hydrogen. between oxygen, check hydrogen. Oopsies. Check hydrogen right here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so let's go and check the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, here got 9 hydrogen and the other side got 16 hydrogen. So in this case, we will add the hydrogens on this right hand side. H2O, right? So hydrogens, since 16 and 9, or 9 on the right hand side, 16 on the left hand side. So that means we will have to add 7 more. So 7 more hydrogens. We'll put 7 over 2 right here. Okay? Then next we balance the oxygen. So now instead of 15 oxygen, now we have 15 plus 7 over 2. Oh yeah, actually no, before I add the water, I forgot to include that uh there's the charges. So 1, 2, 3, 4, 5. So there are 5 negative charges plus minus 2, 5, well, minus 7. So I will have to add 7 OH right here. I have to add 7 OH minus right here. Okay, 7 OH minus. So this one is got 7 O and plus 7 more H's. It means that we will have 23 H and 7 O on the left hand side. Then now, for this case, we will have, this side will have 9H. This product have 9H. Okay. And to add to this part, right? So 23 minus 9 will be 14. So 14, that means we will have 7. 7 water molecules. 7 number of moles of water molecule. So 7 oxygen plus 3 oxygen from carbonate. 10 oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15. So 22 O on the right hand side. Right hand side have 22 O. That means we will have to add around 15 to the bracket O part. Okay, so this is how you balance the chemical equation for strong oxidation. So first step is you take note of the charges. So balance the charges first. You check the right hand side how many negative charges are there. In this case it's 1, 2, 3, 4, 5, 6, 7. So 7, I have a negative charge of minus 7 in total on the right hand side. So that's why I added 7 OH minus, because the alkaline medium is used. Okay, then the next step is to balance the number of carbon. Number of carbons are balanced on both sides, so it should be all good. Then the third step is to balance the number of hydrogens. So the left hand side have 23 hydrogen, right hand side of the organic product has 9 hydrogen. So that's why I have to balance it out with 7 water molecule. Okay? Then the last step is to balance the number of oxygen. So we have counted there's a total of 22 oxygen including the 7 water molecule right there. So 22 oxygen on right hand side. So and we know that there's 7 oxygen from hydroxide ion. So that's why we added 15 of the bracket O. Okay, so just to summarize, first step, balance charges. If you're doing strong oxidation of in alkaline medium. Second is balance carbon. Third step, balance uh not oxygen, balance hydrogen. And then last but not least, you balance oxygen. Okay, you balance oxygen the last because uh generally oxygens there's a lot of reactant and product that contains oxygen. So we want to deal with oxygen the last. Okay, so that is it for alkenes. Thanks so much for watching, and then we will go to arenes in the next part.